In this problem, I am asked to figure out what H1 and H2 are for these three liquids that we have: water, mercury, and oil. So we are not given in the problem statement the densities of any of these liquids, so we can look them up in a table. And for water, I'm just going to use the approximation that we typically use, which is 1,000 kilograms per meters cubed. For mercury, I had to look it up in a table. It was 13,550 kilograms per meters cubed. And this oil right here is given as a specific gravity. So specific gravity is going to be the density of the oil over the density of a reference, which is water. So I'll get that this is equal to 0.78, which is equal to the density of the oil over my 1,000 kilograms per meters cubed. And I'll get that the density of my oil is equal to 780 kilograms per meters cubed. Now, the other thing, I want to look at this diagram, and I see that each of these tubes are open to the atmosphere. So we have our atmospheric pressure at the top of each of these cubes. Now, if you remember, what we need to do is we need to work our way through the tube. And when we work our way through the tube, if we're going down, we're going to have to add pressure. If we're going up, we're going to subtract pressure. And if we're going side to side, there's no change in pressure. All right, so I want to figure out what H1 is. And to figure out what H1 is, I'm going to start with this pressure right here, and I'm going to work my way down, and I'm just going to go like this. And work my way from this pressure to this pressure. So I'm going to start with an atmospheric pressure, P ATM. I'm going down through water, so I'm going to have to add my density of water times gravity times whatever this height of the water is. And the height of the water, let's see where I can put it, right here, is going to be 0.27 meters. Okay, so now I'm at this part, and I want to keep going down. I don't know what H1 is, so I want to solve for it directly. I don't want to cut over or anything like that, so I'm going to say plus my density of my mercury times gravity times the height right here of H1. So now I'm at this point. I'm going to go over horizontally, and now I'm going to work my way up. I'm still in mercury, but I'm going up, so it's going to be minus my density of mercury times gravity times whatever this height, we'll say height of mercury is. And this is going to be equal to 8 centimeters or 0.08 meters. So now we're up here and we're at atmospheric pressure. So this is equal to atmospheric pressure. Well, let's simplify this and put in our values. Atmospheric pressure on both sides of the equation will cancel out. And now I'm going to have 1,000 kilograms per meters cubed times 9.81 meters per second squared times 0.27 meters. And we want to do a quick unit check right here. So what this is, looks like this unit is going to be weird. So I'm going to have a kilogram. I'm going to have a meters cubed. I'm going to have a meter. I'm going to have a second squared. And I'm going to have a meter. These meters are going to combine. So we're going to have meters squared. This is going to cancel with 2 of those meters. So we get a kilogram per meter second squared. Okay. Well, let's look at what a Newton is, or a Pascal. A Pascal is a Newton per meter squared, and a Newton is a kilogram meter per second squared. Okay, so we can see that these are equivalent. So if I take this and simplify this, I get this as a kilogram per meter second squared, which is the same as what this unit is. So that's good. They're units of Pascal, which makes sense, and because I'm working with pressure. So I'm going to have plus 13,550 kilogram per meter cubed times 9.81 meters per second squared times H1 minus 13,550 times 9.81 meters per second squared times this height of Mercury, which is 0.8, and that's equal to 0. So let's put this in the calculator and let's calculate it. All right, then we'll do this. Bring it over to the other side of the equation. Then we'll divide out the Mercury and we'll solve for H1. And we'll get H1 is equal to 0.06 meters or 6 centimeters. Okay, great. So now I want to figure out what H2 is. And there's a few ways you could go about this. You could go back from H1 and then go up to H2. But I'm just going to start at this atmospheric pressure right here and work my way through this part of the U. So again, both sides are open to the atmosphere. So I'm going to have P ATM. I'm going to be able to take advantage of the fact that I have Mercury right here. So the only part I need to add in is going to be this 3 centimeters right here. So I'm going to have plus my density of Mercury times gravity times the height of Mercury, and I'll say this is underscored. It's really 2. Mercury prime. So the height of Mercury prime is 0.03. And I can do that because this is a single liquid, and I'm going to go down at this point. And when I go 3 centimeters down, now my liquid is all the same. So if I went 8 centimeters down, I would then go 5 centimeters back up, and it would just cancel out with 5 of the centimeters that I went down, and I would be left with a net change of 3 centimeters. Okay, so I went to here, and so now I can go up. If I'm going up, I'm going to subtract. This is going to be the density of my oil times gravity times H2, and then I'm at my second atmospheric pressure. Again, my atmospheric pressures cancel with each other. Let's put in my numerical values. So 13,550 times 9.81 times 0.03 meters minus 780 times 9.81 times whatever H2 is. And this is equal to 0. So let's solve for H2 and finish this problem. 13,580 times 9.81 times 0.03. We're going to move it to the other side of the equation. Then we're going to divide by minus 780 times 9.81. And we get that H2 is going to be equal to 0.521 meters or 52.1 centimeters. And that is what this problem was asking for. So hopefully this has helped you understand how hydrostatic fluids work and how we can work our way up and down a system, adding and subtracting pressures.